If A is a square matrix, then A dot adjoint A is equal to adjoint A into A is equal to determinate into I. Proof. Let A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Then adjoint of A is equal to A cofactor A11, cofactor A21, cofactor A31, cofactor A12, cofactor A22, cofactor A32, cofactor 13, cofactor A23, then cofactor A33, then A into adjoint of A is equal to determinate A 0 0 0 determinate A 0 0 0 determinate A. Why it comes to determinate? This row into this column. That means this element multiplication which is this cofactor. That means element with its corresponding cofactor. Okay, elements with corresponding cofactor, elements with corresponding cofactor, its sum is equal to determinate. That's why similarly, this is also determinate A, this is also determinate A. If you taking common determinate A, that is 1 0 0 0 1 0 0 0 1, that means it is a determinate A into identity. Similarly, adjoint of A into A is equal to determinate A into identity. Hence, A dot adjoint A is equal to adjoint A dot A. That is equal to determinate A into I. Now, singular matrix. A square matrix A is said to be singular if A determinate is equal to 0. That means if you take one example, A is equal to 1, 2, 4, 8. So, determinate A is equal to 8 minus 8 equal to 0. So, the A is a singular matrix. A is called singular matrix. Now, definition of a non-singular matrix. A square matrix A is said to be non-singular if determinate A is not equal to 0. If A and B are non-singular matrix of the same order, then A into B and B into A are also non-singular matrix of same order. Another theorem, the determinate of the product of matrices is equal to the product of their respective determinants. That is, determinate AB is equal to determinate A into determinate B, where A and B are square matrix of the same order. Now here note, adjoint of A dot into A is equal to determinate A into I. That we know. Here A is a 3 cross 3 meter you take. Let adjoint of A into A is equal to determinate of A into identity. You take both side determinate. Now here adjoint of A into A का determinate is equal to identity value 1 0 0 0 1 0 0 0 1 डाल दिया. So that after multiplication determinate A, it comes to determinate A 0 0 0 determinate A 0 0 0 determinate A. Hence, that is equal to determinate A whole cube. Why? That is taken common from one row, then this row, then this row. After the determinate A का whole cube हो गया. Then remaining 1 0 0 0 1 0 0 0 1. Then that's why this value is equal to 1. So the adjoint, ये determinate का rule जो था, A B का determinate is equal to A का determinate into B का determinate. That formula we have to apply here. The adjoint A का determinate into A का determinate is equal to determinate A का whole cube. Then one determinate is got it. Now it's come to the adjoint of A का determinate is equal to determinate A का whole square. According to this technique, now we get if A is a square matrix of the order n, then adjoint of A का determinate is equal to determinate A to the power n minus 1, where n is the order. Properties of adjoint matrix. A into adjoint of A is equal to adjoint of A into A, which is equal to determinate A into I. Adjoint of A का determinate is equal to determinate A का to the power n minus 1, where n is the order of A matrix. Adjoint into adjoint of A, that is equal to adjoint of A is equal to determinate A to the power n minus 2 into A, where n is order of A matrix. Adjoint of B is equal to adjoint of B into adjoint of A, not equal to adjoint of A into adjoint of B. Here adjoint of A whole to the power transpose, that is equal to adjoint A transpose. Adjoint of K into A is equal to K to the power n minus 1 adjoint of A, where n is the order of A matrix. Now adjoint of A का determinate is equal to determinate A का to the power n minus 1 whole square, where n is the order of A matrix. Theorem: a square matrix A is invertible if A is non-singular, means if IFM means if and only if. Proof: let A be invertible matrix if order n let A be an invertible matrix of order n and I be the identity matrix of order n, then there exists a square matrix B of the order n such that AB is equal to BA is equal to identity. Now AB is equal to identity, AB का determinate is equal to identity का determinate. That means A determinate into B determinate is equal to 1. So A determinate is not equal to 0. Hence A is non-singular. Conversely, let A be non-singular, that means determinate A is not equal to 0. Now A into adjoint of A is equal to adjoint of A into A, that is equal to determinate A into identity. So now you divide the determinate A both the side. That means A into adjoint of A divided by determinate, adjoint of A into divided by determinate into A, which is equal to identity. Means here determinate A divided. Here AB, that means that equal to AB is equal to BA is equal to identity, where B is equal to adjoint of A divided by determinate of A. So A is invertible. Hence B is equal to A invert, that is equal to adjoint of A divided by determinate of A. If A is, take one example, if A is 1 3 3 1 4 3 1 3 4, then verify that A into adjoint of A is equal to determinate A into identity. And also find A inverse. We have determinate is equal to, here determinate you have to find out determinate, that is equal to 116 minus 9 minus 3 into 4 minus 3 plus 3 into 3 minus 4, which is equal to 1. That means this is not equal to 0. This is not equal to 0 means it is a non-singular. So it is invertible. Now you have to find out the cofactor, minor and adjoint. How? So taking the elements 1, 3, the element is say that row as element, that is the row element, this row element, this is row element, this row element, that is this row element. And what the minor? You have to find out the minor. How? This is 1 ka minor, that is a corresponding row column deleted, therefore 3, 3, 4. Similarly, this is 3 ka minor, that is corresponding row column deleted, 1, 3, 1, 4 ka, okay, determine. That means 1 comes. Similarly, this the minor is 3 ka minor minus 1, 1 ka minor 3, 4 ka minus 1, 3 ka minus 0, 1 ka minor minus 3, 3 ka minor 0, 4 ka minor 1. Then sign minus 1 to the power I plus j, that is row plus column. That sign first you take positive, then rotate. Negative, then positive, then negative, then positive, then negative, then positive, then negative, then positive. Similarly, this into this, that is the cofactor. Cofactor is equal to minus 1 to the power I plus j into minor ij. That is aij or Cij. Simple, this multiplies with this multiply with this. So this multiply with this. So this multiply with this. So this multiplied with this, it comes. So that means after taking that minor into sign, it comes to cofactor. Then this is the cofactor. Now cofactor matrix is equal to what? So whatever the row you return, that is according to row wise. That means this 1 ka cofactor 7, 3 ka cofactor minus 1. So that same way that you have to write what the cofactor. After writing that, it comes to a what na cofactor matrix. Then cofactor matrix ka transpose, that is the adjoint. Means this row comes to column, this row comes to column, this row comes to column. It converted to adjoint now. A into adjoint, that is this is A, this is adjoint. Then after multiplication it comes to 7 minus 3 minus 3. Okay, then this value comes. After multiplication, this value comes. So, this value gives to this is equal to 1, this is 0, this is 0, this is 0, this is 1, this is 0, this is 0, this is 0, this is 1. That means it is converted to identity. It is converted to identity. That means which 1 0 0 0 1 0 0 0 1 means you take common 1 into 1 0 0 0 1 0 0 0 1. Here 1 value is determinate A. That's why determinate into identity. So A inverse is equal to adjoint of A divided by determinate A. That is equal to adjoint of A is equal to 7 minus 3 minus 3 minus 1 1 0 minus 1 0 1. But determinate ka value 1. So after dividing that, the value 7 minus 3 minus 3 minus 1 1 0 minus 1 0 1. So that is the A inverse. Now A inverse got. Please subscribe the channel for more update video.